Hi, this is Math 1350, and this video is over section 1.3. It's actually the second part to this. We're going to look at symmetry, and then we're going to look at the difference quotient, which difference quotient is a huge thing in calculus. Alright, so symmetry, there's three types, three main types when it comes to functions. You got a few other types in a sense when like if you look at a quadratic, it can be symmetrical to something else besides the three we're going to be looking at. First one is if it's symmetrical to an x-axis. So that's this last one here. All right, the x-axis acts as a mirror. Notice it's not a function, doesn't pass the vertical line test. All right, anywhere on this graph. So not all symmetry has to do with being a function. Some just have to do with the way the graph looks. The next one is when it's symmetrical to the y-axis. So that's this last, the first one here. And for those are what we call even functions. So when you see polynomials that have x squares, x to the fourth, or even just a constant number, and only have those, you know there's going to be symmetry with the y-axis. And then the middle one, the odd functions, these are symmetrical to the origin, and these happen when x is being cubed, or just regular x, or x to the fifth when it comes to polynomials. Plus the odd functions can happen, I've seen, with rational functions. So that's why we're going to end up finding a way to test it. So because sometimes you can see it just from looking at the equation, other times you actually have to test it. Okay, now to test for symmetry with the x-axis, you replace your y with a negative y, and the reason why is because xy has to line up with x negative y. So if you replace y with negative y, you should still end up with the same x, which means you should still end up with the same function. With symmetry to the y-axis, you replace x with negative x, and that's because if you have x and you get y out, then when you plug in negative x, you should still get y out, so you should still end up with the same function. And then for odd functions, we replace x with negative x and y with negative y, and that's because, you know, xy, if you plug in negative x in place of x, then you should get a negative y out. Alright, so we'll do these tests. Right, now notice this one's a constant and an x squared. So this is an even function. Okay, so it should be symmetrical only to the y-axis, but we're going to go through all three of these. So we go for the first one, we just replace y with negative y, and so we end up with negative y plus x squared. And so I'll try to factor out negative x, and so we don't end up with the same function. We end up with the negative of that function. So this is not symmetrical to x-axis. Okay. Test for y. So replace x with negative x. When I square it, I get the exact same function out. Okay, this is symmetrical to y-axis. And you can graph it if you want, and you can see it. Then we can look at the origin. We replace y with negative y and x with negative x. And so we get more something like the first one, where you just don't get the same function back. So not symmetrical to origin. So 4x minus x cubed. Notice this is an odd, this is an even. This should not be, it's not symmetrical. Okay, but we're going to test these. So for x, we'll let y be negative. And so we just end up the negative of the function. So not symmetrical to x axis. For y, we let x be negative. And so we end up with negative 4x minus x squared. So negative 4x plus x squared. This is not the same function, so not symmetrical to y-axis. And test for the origin. So divide over the negative, we get 4x plus x squared. Still not the same thing. So not symmetrical to origin. Okay. Now, rational functions are a little different. I would recommend not trying to guess like I did for the other ones. I could see how it was going to end up being. This one, this one you have to kind of test it. Test it either by doing this or by graphing it. That could help. So first we'll start with the first one. Let y be negative. And so you end up with a 1 over x cubed. Not the same thing, so not symmetrical to x-axis. Then we test for y. And we get negative 1 over negative x cubed. So 1 over x cubed. Okay, so not symmetrical to y-axis. And then we'll do the origin. Negative y equals 1, negative 1 over negative x cubed. And so we negative y equals negative 1 over negative x cubed. So negative y equals 1 over x cubed. So y equals negative 1 over x cubed. This is the same. So we have symmetry to origin. And a lot of rational functions will have that. Not all, but a lot will. Alright, so there's two types of functions that have symmetrical to origin. Odd functions and rational functions can be. Even functions are symmetrical to the y-axis, and then certain types of non-functions are symmetrical to the x-axis. Alright, so now we're going to look at the difference quotient. And the difference quotient, I'm going to pull up Desmos on this real quick. And let's see if I can look up. Not logged in. Let me log in. Alright, so there's one I have on here. I had one pull up. Maybe this one will work. No, that's not the one I wanted. is the one. Alright. So we're just going to look at, I'm going to change this regular x squared. Alright. And so we got 2 points here. Point A is going to be where you have an x, and f of that x gives you that point on this graph. And so if we say this is 4, then our value at 4 is about maybe 16, around 16. All right, and then we have point B, and this is x plus h, so it's h away, and it's that point's up here, that's blue. And then we have a line that goes from A to B, that's yellow, that's your secant line. Okay, and you can see that the secant line is close to the same slope as the graph here. Okay, and so we're going to use this idea that that secant line is close to the same slope as the graph in order to find the slope of this curve, or to estimate the slope of this curve. And that's what we call the difference quotient. Now, of course, if we would take this point and really go higher, that doesn't want that, let me go up, then it ends up being a little bit farther off. We bring it down, and it ends up being even closer. You can see it gets really close until we're almost on the line. So when it get all the way down to it, our secant line isn't a secant line anymore, it's a tangent line. Okay, so that's the idea with this. Now, the algebra part to this is actually the hard part. The calculus part is easy. Once you do the algebra, then we let h equal 0, and we plug that in. The problem is our h is in the denominator, and the reason why we have that, okay, we're finding the slope of the secant line. So we're looking at a graph where this is x, and this is f of x, and this is x plus h, and up here is f of x plus h. And we're finding this slope to see if it represents, or estimate the slope of the curve. Okay, and so slope is just y2, so f of x plus h minus y1 f of x over x2 x plus h minus x, and so you end up getting f of x plus h minus f of x over h. Okay, and so that's how that comes about. Okay, so we gotta do the algebra to get this h to divide out. Alright, so we're going to start with a linear one. Now, we're finding the slope. So with a linear line, what's the slope? Slope is equal to 2. So we should end up with 2. So we do 2 x plus h minus 7 minus 2x minus 7 over h. Right. Now we'll distribute the 2, get 2x plus 2h minus 7, distribute negative sign, you get negative 2x plus 7. Right, all over h. So now where we see it cancels, 2x cancels with that negative 2x, negative 7 cancels with that 7, we end up with 2h over h. H is divided out, you get 2. Exactly what we expected to get. Okay. Linear lines, all line, it has a slope. Slope is the same as the line that would be secant to 2 points on it. Okay, the linear line is technically a secant line between its 2 points, or any of its points. Okay, let's do the next one. X squared minus x. So we'll have x plus h squared minus x plus h, then minus x squared minus x all over h. Okay. So now I'll do that here. We'll FOIL out the x plus h, distribute the negative signs, and look at what cancels. So x squared plus 2xh plus h squared minus x minus h minus x squared plus x all over h, and x squared cancels with x squared, x negative x cancels with x, and that should always happen. What's your original function, the terms in it should always cancel. So you end up with 2xh plus h squared minus h all over h. This allows us to factor out an h. Oops, took away that h. So factor out an h, I get 2x plus h minus 1. Divide out those h's, I get 2x plus h minus 1. And calculus part of this would be to let h be 0, and then you have 2x minus 1. But we're going to stop here, the algebra part. Right, last one, 2 over x minus 2. Now, this is going to require, since we're dealing with rational functions, going to require completing a common denominator. We're going to end up having to find a common denominator. Unfortunately, it's not going to be a nice little common denominator either. But I'm going to try to make this as simplified as possible. So 2 over x plus h minus 2 minus 2 over x minus 2 over h. So we're going to find the common denominator, which is just multiplying the right by the denominator on the left, and multiplying the left fraction by the denominator on the right. Okay. So what we have on top, we have 2 times x minus 2 minus 2 times x plus h minus 2. Denominator here, we have x plus h minus 2 times x minus 2. And then that h in that denominator actually will end up on the bottom here as well. If you don't believe me, you can multiply top and bottom by 1 over h. And you'll see that it ends up on the bottom. Alright, so distribute the top, 2x minus 4 minus 2x minus 2h plus 4. Okay, now what cancels? 2x cancels that 2x, 4 cancels the 4. So we have a negative 2h over h. And now you should be able to see we can cancel the h's. So we end up with a negative 2 over x plus h minus 2 over x minus 2. And so now when h is left let to be 0, we actually get an expression. Alright, so that's going to be it for this part. The next one we'll look at section 1.4 and 1.5. I'll see you then.